All right, now we can take into account the influence of uniformly distributed loads. So in terms of reactions, this is going to be, again, very similar to how we dealt with point loads. So you can see we've got our structure here. Now, in the actual target structure that we're aiming to ultimately analyze, we don't actually have a uniformly distributed load. We have a load of varying intensity, linearly varying intensity. So for the purposes of sort of demonstrating how we're going to handle the calculation, I've just applied a distributed load on our structure over the same location of where our linearly varying distributed load is in our target structure, shall we say. So how are we going to deal with this? Well, the first thing, because it's a distributed load, the first thing that you're always going to do is work out what's the resultant force and what is the location of that resultant. So we'll try and keep our calculations here, or not so much our calculations, but we'll keep our expressions in terms of the symbols that we've got here. X start for the start of the distributed load, x end for the location of the end of the distributed load, and fy being the magnitude, the constant magnitude. All right, so let's call the resultant fy underscore res, and let's have a capital R there, res. Now how are we going to work that out? Well, that's pretty trivial, right? So that's just going to be fy, the magnitude, times the length over which that force acts, which is just going to be x, let's stick with a lowercase, x end minus x start. All right, so that's going to give me the resultant. So that gives me as if I took away that uniformly distributed load and replaced it with a single point load. If I did so, that point load would have magnitude fy res. All right, great. The next thing I want to do is I want to know where is that resultant, at what position along the beam is it, right? So let's just highlight or identify the location on our diagram here. So let's draw a line there, and let's call that, what did we call that? X, probably x underscore res. Okay. So where is this thing positioned, right? So x underscore res, well, that's again fairly straightforward. It's just going to be x start plus half of the distance between x start and x end, right? So we'll have x end minus x start. All right, so that gives me x res. Okay, so once we work out where the resultant is and what the magnitude of the resultant is, working out the reactions is exactly the same as when we were dealing with a point load. So that's basically all we have to say here. We're not going to spend any more time discussing it, because when we get over into our Jupyter notebook, we're going to basically just take the code we wrote for our point load, make a couple of minor edits to reflect these terms here, fy res and x res, and it's basically going to be the exact same logic. So we can draw a line under that. So then we move on and we start thinking about, okay, well, how do I deal with the moment? How do I deal with the moment and the shear for this scenario where I have a uniformly distributed load? Now, there are two cases to consider. Either my cut, well, I guess there's three cases we could consider, right? So we could imagine if our cut was here, right? Well, then it's to the left of the point load, i.e. x, the location of the cut, is going to be less than x start, in which case, obviously, the uniformly distributed load isn't going to appear in a moment equation when we're evaluating the moment at that cut. When we look at the substructure to the left of the cut, so nothing to evaluate. The next case where we do have something to evaluate is if we have our cut somewhere between x start and x end. So we're going to want to develop an equation that calculates the shear force and bending moment in that scenario. And then it doesn't happen on this beam, but the third case would be, let's imagine this beam continued off over to the right here, and we wanted to make a cut somewhere over here, in which case the location of the cut, x, is all the way to the right, past the end of the uniformly distributed load. So in that scenario, we're going to have a different equation that's going to give us the shear force and bending moment. So really, we're going to focus in on this case here where we've got that cut, and this case here where we've got that cut. So we're going to develop two pairs of equations for the shear moment in each case. All right, so let's just get on there and start working this out. So let's think about the first case where we're making our cut actually in between x start and x end, somewhere along the length of that uniformly distributed load. We've got a cut in there. So let's just sketch out a rough sketch of what that might be and what are the main parameters. So we're going to have the distributed load here like this. we're going to have a vertical cutting plane in here, and the relevant parameters are going to be x start. We're going to have, let me see, let's draw on the resultant. Now the resultant in this case is only going to be the resultant of the load to the left of the cut, right? So that's going to be your resultant, and of course it's going to have a lever arm, which is the distance, the perpendicular distance between the line of action of the force and the vertical cutting plane. All right, let's just call that my lever arm. What else have we got? We've got to represent x, the distance over to the cut. Right, so that's going to be x. Right, so what are we going to have, right? Well, actually, let's just be explicit here. This is when x is greater than or equal to, let me see. Yeah, when x is greater than or equal to x start, and when it's less than or equal to x end, right? So that's the scenario that we're taking account of here. So what would the shear be? Well, the shear at that cut would be, well, it's simply all of the force to the left of the cut, right? And all that is going to be whatever the magnitude of the distributed load is, the uniformly distributed load, times the length over which it acts. It's just the amount of load to the left of the cut. So it's going to be Fy, and then the length over which that load acts is actually going to be this length in here, and we can get that from x minus x start. All right, and then the moment is simply going to be, it's going to be a minus this time. So it's going to be the actual load, same as the shear, x minus x start times Fy, times the lever arm. And what's the lever arm? Well, the lever arm is just half of the distance over which the UDL acts, because obviously it's a uniformly distributed load, and therefore the resultant acts halfway along. So in this case, the lever arm is going to be half of x minus x start. All right, so that's essentially our equation for our shear and moment in the scenario where we're making our cut somewhere between the start and the end of the distributed load. And then the second scenario is when x, the cut, is going to be some point past the end of the UDL. So when x is greater than x end, right? So that's the case that we're interested in now. So you just have your beam here, you've got a vertical cutting plane here, and we're saying that our distributed load finished up some point to the left of where I made that cut. Okay, in which case, let's draw on the resultant. There's your resultant, and there's your lever arm. What else have we got? Well, we've got the location of the cut, which is all the way over to the right, which is just x. All right, what's the shear and moment this time, right? The shear is going to be, again, the force F, what did we call it? We called it Fy, and this time it's the full length over which that force acts, which is the full UDL, so that's going to be x end minus x start. All right, that's your shear. Your moment is going to be minus Fy, so the full force times its lever arm. So what's the lever arm this time? Well, the lever arm is going to be this distance in here. So how do I get that distance, right? That distance is going to be, one way of getting it is, it's going to be x, right? The total distance. Take away this chunk here, x start, and then take away this little chunk here, which is half of x end minus x start. So that's your lever arm in this scenario. So let's say times x minus x start minus 0.5 times x end minus x start. All right, so that's my second pair of equations for my shear and moment. So now all we have to do is implement them over in our Jupyter notebook. So we'll jump over to the notebook and do that now. All right, here we are over in the notebook. We're going to follow a pretty well-worn path now at this point. So again, let's start off. It's the same process every time, right? So what did we call this? I think we're going to call this distributed loads this time. Distributed loads. Now this is going to be for, let's fix the note. Let's come in, let's actually get rid of that and define a new distributed loads. And let me see, it's going to be an array. Now what are we defining for a distributed load? We want the position that the load starts at, the position that it ends at, and then the magnitude, the constant magnitude. So in this case, it starts at 8 meters, it goes all the way to 17 meters, and it has a magnitude of, let's just say minus 10. So it's 10 kilonewtons per meter acting down. All right, let's come along and work out the number of distributed loads that we have to deal with here. So let's call this NUDL for uniformly distributed load, and that's going to be the length of distributed loads and 0. And we'll just say test for uniformly distributed loads. Now, while I'm fixing notes here, let me come up here and correct this note. So that should say x start, x end, and the magnitude can be the same. That's fine. Right, let's come on down and build a function to calculate our reactions. So we'll come in and drop it in just below where we defined our last function for calculating reactions. I'm going to copy the name here, or the title. So define a function to calculate reactions due to, let's just say UDLs. All right, great. So what am I calling this function? I'm going to call it reactions underscore UDL. Again, it's taking n. All right, and we're going to extract out x start. We want x end. And let's define Fy as being the magnitude of the distributed load. All right, so let's work out the resultant, because as I said, it's going to be, let's hide this code. Let's bring back this code. So it's going to be pretty much exactly how we dealt with a point load. It's just that the little step we have to do before we do this is to work out what's the magnitude and location of the resultant, which essentially is a point load. So we'll say Fy res, and that's going to be equal to Fy times the length over which it acts, which is going to be x end minus x start. And we'll say x underscore res, the location, is going to be x start plus 0.5 times x end minus x start. Excellent. And at this point, we're more or less going to do the same thing as we did for our point loads, but we're going to have to be very careful that we make the updates that are necessary, right? So let's go down through this carefully one by one. So the lever arm of our point load now is going to be a minus x res, okay, because x res now identifies the location of that resultant point load. So resultant, so that's the lever arm of, let's just say, resultant point load about point A. Now MP is going to be, it's going to be Fy res this time, okay, times LAP, and that's the moment generated by resultant point load about A. That's okay. And then LA VB, the lever arm of VB, is it going to be the exact same as usual? Okay, so VB is then going to be, okay, that's fine. VA then is going to be Fy underscore res minus VB, and of course there is no horizontal reaction coming from a vertical uniformly distributed load, and then we just have to return out, as usual, the values. So we'll return VA and VB. Brilliant, so that's our function defined. Let's come along then and do our usual trick of cycling through each of the uniformly distributed loads. Okay, let's copy this down. So I'll cycle through all UDLs and determine reactions. So again, I'm going to copy all of this, drop it in here, and then make my amendments, right? So what am I dealing with? I'm saying PM, let's call this, instead of PM, let's call this UDL record. And everything on the right hand side is fine. Now this is going to be UDL. Obviously we need to cycle through the distributed loads now. And I think what did we call that? It was UDL, right? So yeah, UDL. And then UDL record is going to be appending onto UDL record, and the rest of that's okay. All right, so that should be our reactions calculated. So I should be able to, okay, NP. I haven't run this from the top yet. Okay, so let me run all the way down, shift enter, shift enter. Okay, excellent. So now I'm going to skip over all of this and jump down to the end and just execute this. And we've got 4.8 or 4.5 and 85.5, which is correct. Right, so now we can get on to the next step, which is calculating the shear moment. Let's define the function in the usual way. Another new cell. copy this guy here, bring him down here, change it to a markdown cell. Define function to calculate shear forces and bending moments due to UDLs. All right, excellent. So let's define our function. So this is going to be shear underscore moment underscore UDL. It's taking in n. All right, and we're going to start off by extracting out x start. Do I have that done already? I think I've done that already, right? Yeah. Okay, so let's extract these guys out. So x start, x end, and fy, and then we want the reactions. VA is going to be UDL underscore record, and we want n and 0. And let's do the same to get VB. It's going to be n and 1. Now, we said we were going to, let me see, this is going to be very similar to pretty much every time we've done this. It's going to be pretty similar. So let's come in here and take out all of this again. Come on down and drop it in here. Right, so we're defining a bucket of zeros for shear and moment, which we can override. Of course, we need to change these notes. Right, so all of this is the same. That's the same because that's just calculating the shear and moment due to a reaction at A. That's the same for our reaction at B. This is where we need to change things up a little bit. So we're going to have a first condition that says, let's just get rid of that condition. So if the cut x is greater than x start and x is less than, let's say less than or equal to x end, right? If that's the case, well, then we're cutting through our distributed load. So our shear is going to be whatever it was previously, plus, based on the equations we've already looked at, Fy times x minus x start. And the moment can be whatever it was previously, minus Fy times x minus x start. So that's the force, and then it has to be multiplied by a lever arm, which was 0.5 times x minus x start. Okay, now so that's one condition taken care of. We have another possible condition, so we'll say L if x is going to be greater than x n. So if we're to the right of the uniformly distributed load, well then shear is going to be shear plus the full force, the full effect of the UDL, which was going to be Fy. So it's intensity times x end minus x start. All right, and the moment is going to be the moment minus the same force, right? So it's the same force times the lever arm. Now the lever arm in this case, as we said, was going to be x minus x start minus 0.5 times x end minus x start. Excellent. So that's your moment, and the rest of it can stay the same. So that should be, provided there's no typos in there, that should be our function calculated. Now let's just do the usual, build a function to cycle through, or build a for loop, I should say, to cycle through. So again, copy this guy, come in here. So cycle through all point moments, it's not point moments, it's UDLs, to determine the shear and moment. All right then, so in this case, if n UDL happens to be greater than 0, let's come in and do the usual. So I'm going to copy all of that, drop it in there. This needs to be changed to distributed loads. This needs to be shear underscore moment underscore UDL. And then the rest of it can stay the same except for our notes. All right, that should be it. That should be it. Let's just run this thing and see what we get. Right, so running it from the top. Okay, excellent. So here's our shear force diagram. So remember, we said the uniformly distributed load started at 8 meters and continued constant magnitude all the way off to the end. So we look at our shear force diagram, right? We have that 4.5 reaction, kilonewton reaction, pushing the shear force diagram up at the reaction at A. Nothing happening on the beam between A and all the way over until the UDL starts, and so the shear force remains constant. Then the UDL comes on and starts reducing our shear force diagram linearly all the way over until bang, we hit the reaction at B, and because it's a point load, it causes a step change in the shear force diagram, and so we step straight up The total magnitude of that step was whatever the reaction was. I think it was 85.5. So that brings us up to, let's call it 30, let's call it 40. And then our UDL is continuing to draw it back down. So you'll notice the slope of this line here is the same as the slope of this line here, because it's the effect of the UDL causing that shear to reduce linearly all the way back to 0 at the free end over here. So before we even look at the bending moment diagram, think of what we expect it to look like, right? So we've got a constant shear in this region here, which means we're expecting a linearly varying bending moment diagram in that region. Again, the shear force here is a positive shear force, and so we're expecting the slope of the bending moment diagram to be a positive value. Then we have a linearly varying shear force, which means the bending moment diagram, as always, is going to be a polynomial of one order higher. So it's going to be a curve. It's going to be a curve all the way from here all the way over to here. Now we see that the shear force starts off as positive, then goes negative, and that means that the slope of the bending moment diagram will start positive and the slope will then turn negative at this point here. And so again, we've got 0 shear here, and so that's also going to be a local maximum or minimum in our bending moment diagram. Okay, so we're going to be sloping with a negative slope all the way down to here. We're going to see a step change in the shear force diagram, which really means there's going to be a change in the sign of the slope in the bending moment diagram, but again, it's going to be curved. So you're going to have some kind of a peak down here where the slope changes from being a negative slope to a positive slope on the right hand side. So let's, with all that sort of information baked into that shear force diagram, let's go down and look at the bending moment diagram. All right, excellent. So what are we seeing? We've got a linearly changing bending moment diagram, as we'd expect, all the way down to 8 meters down here. The slope remains a positive slope. Notice that the bending moment diagram is positive downwards here now, right? So that slope is actually a positive slope until we get to a local maximum, and the slope changes sign after the local maximum to be a negative slope. And again, emphasizing here that the bending moment diagram is positive downwards, and so a negative slope does indeed, point the line back up this way. So we have a negative slope, until we get to this point here. And remember, we said there was going to be a peak in our bending moment diagram where the slope changed from being a negative slope to a positive slope. And sure enough, after that peak, we have a positive sloping bending moment diagram all the way down to 0. So down to 0 here at the free end, which is what we would expect. So there you have it. Yeah, we have our bending moment diagram and our shear force diagram. So it's quite nice. Now, I haven't done it yet, but the nice thing about all this is that we could go all the way back to the top here, and we could undo all the commenting of our actions, right? So let's come to the top, and so we've commented out this. So let's just look and see what would the influence of all of these acting together be, right? So let's uncomment those and then run the code again. All right, excellent. So there's your shear force diagram, and there is your bending moment diagram. So you'll notice already, if you think back to the original structure that we're trying to model, that we're basing this code on, we're starting to get very, very close to the bending moment and shear force diagram that we would have, or that we did have for that original structure. Now, obviously, in that original structure, we had a linearly varying load between 8 meters and 17 meters, and here we've got a constant magnitude load. So they will be different bending moment and shear force diagrams, obviously, but just to say here, we're getting close to our target. So in the next video, we're going to start taking into account the final type of action on our structure, and that's a linearly varying force, or a uniform, or a distributed load of a linearly varying magnitude. And at that point, we'll be able to exactly model the structure that we were basing this whole exercise on, and of course any other simply supported structure we like. All right, so we'll pick it up in the next one.